Hi, everyone. Thank you so much for coming. Very welcome. My name is Erik Hellman. I am a software engineer and freelancer, and I'm going to talk to you today about IoT development with Kotlin. So, hope you're all ready for that. Now, the whole IoT thing is very, depending on who you ask, you get a lot of different answers. But the thing that we are seeing is that we are getting more and more capable hardware into smaller and smaller devices. So and a lot of them are connected, and a lot of them are connected all the time. And well, they help us out at home a lot. Maybe not the dogs here, but maybe you have a robot vacuum cleaner, maybe you have a robotic lawn mower, maybe you have a connected house appliance, etc., etc. And my talk here today is about what if we run Kotlin on these devices? Could we do that? How would it work? What are the challenges? And that's what we're going to talk about today. This is not going to be a deep dive into specific technologies per se. I'm going to talk about them and mention them and recommend some of them and tell you to not use some of them. So I'm going to cover a wide area here because this is a very big field. So where does this come from then? Well, I currently work as a freelancer for a company where I work with robots. Now, this robot is cool. It's not this robot I'm working with. Although this would be really awesome to work with. I would like to have one at home. Now, my robot is more like that one. It's an autonomous piece that runs around in your home, and it carries knives. And you're like, oh my God. They let him on stage? Well, it's actually this one. So it's less scary. The other one comes in 1,000 years. You all know that, right? So you don't have to be scared about that yet. So while I was working with this one, we were also doing a lot of Kotlin on the backend side and on the apps side at this company. And I was thinking, we're getting more and more powerful hardware in these connected devices. So let's see what can we do with it. Now, we're not running Kotlin on this one here specifically, because we can't, and they won't allow me. But I've been trying other ways to do it. So what is an Internet of thing? What is an Internet thing? We need to define that first before we continue here. Well, the robot lawnmower is pretty typical one. It's when I talk about these things, and it's connected. It runs around autonomously. It has very little user interaction on the mover itself. And yeah, it runs pretty advanced software as well. But it could be your smart home lock. It could also be like your home router is basically an Internet of Thing. It doesn't have an interface per se. You interact with it with other devices, usually through a web interface maybe. You're a robot, you're a vacuum cleaner at home. A lot of us have those today. Very helpful, as long as they can avoid the socks. My laundry machine comes with these smart things connected, and I was first very questioning why would I need that, and then I realized because it tells me when it's done. And that's actually super valuable, and that's actually the most common thing you want to do. You want to check how it's doing, how long time is it left, etc. And that goes for other household appliances. Let's say you turn on your oven, you want to know when it's preheated and is done, because maybe you just want to run out or you're not in the kitchen all the time. And also smart plugs, for instance, for all kinds of things. So these are Internet of things, mostly related to your home. Another different thing that happened lately, a couple of years, is that we're moving from doing these Internet of Things stuff on microcontrollers, like the ESP32, but there are other kinds as well. And we're moving to embedded Linux, which makes all of a difference. Basically, you got the hardware of a smartphone inside these devices today, which is great. It's an ARM v8 platform, like the Raspberry Pi here. That allows us to do so much more. Anyone here done microcontroller programming, you know that you're very limited. It is cool, but it does one thing. Usually does that thing well, but can't do other things. So it's not multi-purposing. And a lot of these IoT devices we have are becoming more and more capable. Maybe they have a camera, maybe they're doing AI, etc., etc. So they need more hardware, and therefore, embedded Linux. It's also a cost thing. You can put multiple microcontrollers into doing multiple things, But then the cost benefit of a microcontroller just kind of goes away. It's just better to take one single embedded Linux board, ARM V8 platform, and you can save money that way. And it's also like easier to develop for. Much easier to find developers. And maybe you can run Kotlin on it, right? So IoT with Kotlin. This is IoT with Kotlin. It runs Linux. It has no or very limited HMI, user machine interface. There might be buttons on it. There might be a small display for showing status. But there's no touch screen. There's no real keyboard, et cetera, et cetera. Interaction with that device happens through another device, usually your smartphone. And another important difference here compared to like your smartphone is that this one is always connected. Why does it always need to be connected? Well, when you're not home and you want to park the lawnmower or start your vacuum cleaner or start your laundry, for instance, then it has to be connected all the time or that wouldn't work. It can't be like connecting occasionally to the back end or something then to check if it's going to do something. That wouldn't work. So this is basically our definition of an IoT device when it comes to this talk. Now, so we want to do this. We want to run Kotlin everywhere. And if you're used to Kotlin, you know that, well, it works really well in the cloud for our backend stuff. That's been working from day one. We can run it on Android, or we can also now run it on iOS, so that works well. We can also run it on other clients. We can do desktop, we can do web, et cetera, all in Kotlin. So that's great. The client side for the user-facing stuff is there. So now the question is, how do we get it on embedded Linux? Because that would be very nice. Then we can share code all over. Or at least that's what we're hoping. So there are challenges here. You have two options when you go with this one. Either you go with Kotlin native. That would be the obvious choice at first, right? That was my thought as well. Oh, I'll use Kotlin native. That will be fine. Everything will work out that way. Or you can also run it on the JVM. Because, and you think like, what? You can run the JVM on an embedded Linux? Well, it's basically the same hardware, the same specs as your smartphones. Maybe not the latest generation smartphones, but it's capable there. It has enough memory. Just run the JVM on it, and you're fine. It works great. So we could treat it like that. Just one single JVM running your application, and you can use all the Java libraries. So the compromise here is like, of course, it will use more memory if you run it on the JVM, and you might have the real-time requirements that you lose. But if you have real-time requirements, Kotlin probably is not your choice in this case. Anyway, also if you use Kotlin native, there are not much libraries to use. There are some, but they're missing in the crucial parts. Okay, so communication-wise, we have the communication between your app or your client, your user-facing client, and your backend. That's done usually with HTTP, right? Nothing strange there. When you're communicating with taking the phone and communicating with your IoT device, it's usually Bluetooth. It might be Wi-Fi, but then it comes the problem of setting it up with Wi-Fi. So at some point, there's usually a Bluetooth communication happening. Now, that's one challenge. Anyone worked with Bluetooth, or anyone heard any of my other previous talks knows that Bluetooth is challenging. I like the slow laughter. The despair was present in the air. But yeah, so what about this communication? Well, yes, that's one option. We're getting there. Let's not get ahead of ourselves. Well, yeah, so this is what are the options here, and I'm going to talk a little bit about those. There are several options, and I'm not going to strongly recommend either one of them. I can reveal that now, but we're going to talk about the pros and cons of each. Let's start with Bluetooth, because a talk by me without Bluetooth wouldn't be a real talk. So let's talk about this. What do you do if you want to communicate from a Kotlin Multiplatform app, maybe it's a composed multi-platform app even, and your embedded Linux device. So right off, if you're going to do Bluetooth communication in KMP, you use a library called Cable from Yule's lab. It's great. It solves everything. I've used it now for several projects. There are, at this point, there's no features missing really. As long as you are acting as the central, like in this case, in the Bluetooth world, the phone is the central and there is Raspberry Pi is the peripheral. So when we're communicating, like it acts as a client, then cable works great. If you're going to reverse that one and act as a server in the Bluetooth world, then we don't have any option there. But what you do on embedded Linux, you can't run the cable library there because it's not Android or iOS. This cable library works with Android, iOS, and sort of web browsers where Bluetooth is supported. So what do you do there? So that's the first option. So on Linux, we have the kernel. That's the base thing we got. That's what we call Linux. It doesn't really know about Bluetooth per se. It doesn't know much other than running processes, basically, and allocating memory, writing files, and all those things, basic system things. You build services on top of this that does things that are more complicated, talking to specific hardware or implementing specific services in the UI, for instance. And those services, they talk to the kernel, of course. They do system calls there, open a file, open a network socket, et cetera, et cetera. But they also talk to each other. And this that doesn't scale well if everyone has to implement the interface of another service. So the way it works on Linux is something called dbus. And for those of you who are familiar with Linux, that's completely natural. It's a messaging bus on the system where you communicate with other services that also use this one. And it uses a very well-known addressing scheme that we're going to look at soon. Those of you who are familiar with Android, you might know that there is something in Android called the binder that's similar to the dbus. And for historical reasons, Android does not use dbus. But today, you can pretty much consider them equal in the sense of how processes communicate with each other. So this means we use dbus on embedded Linux in order to talk to a service called BlueZ, or Blues, which is an official standard implementation of Bluetooth on Linux. So your application will talk through the dbus to the Blue service and get the notifications back that way. The dbus is like, it has both this synchronous read and write, and also a subscribe mechanism. So you can subscribe to changes, for instance. So incoming Bluetooth requests can be delegated up to your app if you subscribe to them. So how would we do this? So for Kotlin native, the first option is to use something called Unix domain sockets. Anyone done low-level Unix programming before, you know that Unix domain sockets is basically like a way to use local sockets on the system. And dbus is built on top of Unix domain sockets. So you could just implement everything on Unix domain sockets, and you're good to go. Now, oops, sorry. Now, this requires a lot of code. You will also need to use the POSIX libraries in Kotlin native. And just a single connect method becomes quite large. That's the connect method. So while this is doable, and we might look at doing something like this, it's a little bit too much code to be like manageable. So I don't recommend this, but it's a way to do it. The other way is to use cinterop and the dbus library on Linux. And if you use cinterop, you start with a definition file that you put into your source code. It looks something like this. You might change the path a little bit. You might change the things that are depending on your system. But this is what I used for my Raspberry Pi. It basically takes the dbus header, and then it generates Kotlin code for you, roughly speaking. It's a little bit more than that, but for the sake of purpose here, that's enough. And then you add some Gradle stuff to tell it to generate the code for you, to give it a package name and give it a file, and then it does that on the build. And then you can start working with it. So we write our own wrapper around this, called a dbus. We pass a C pointer with this dbus connection that it generated, and you're good to go. It is still a lot of code, so I skip it here because you have to know and understand how dbus works. We're going to go into that in a moment. Those are the two options for Kotlin native. So what if you run the JVM instead? Okay, so if you're on JVM 16 or later, which, well, obviously we all are, right? Then you can use something called Unix domain sockets, which lets you use a Java library called dbus Java, which is basically a Well, it's a really nice package library for doing dbus communication on Linux from a JVM. Works perfectly, much less code. And if you choose to go the Kotlin JVM way, this is a way to do it. Now, so when you work with dbus, regardless if it's dbus to Java or anything else, the addressing is pretty much the same. So in our case, we define our own service in dbus. We give it a name. That's a service path there. We also have a service UUID, which is specific for our Bluetooth service. We want to start advertising using this service UUID. I'm not going to go into details of how Bluetooth works. Look at one of my older talks for that. And then we initiate this, say, dbus connection, get connection. We want a system bus. There are 2 different dbus instances on the Linux system. And also we have some addresses here. This is the service, the dbus service for Blues. That's the address to it. This is the path to the adapter that we're going to talk to. And this is the interface for the Bluetooth Low Energy advertising manager that you need in order to send advertisements. Then start advertising. You create that object, you export it on the dbus connection, and you say, get a remote object for the Bluetooth service, for the Bluetooth advertising manager, and then you call a method with return. So it's a synchronous method call over dbus, basically, telling, please register the advertisements with these parameters. And the Bluetooth adapter will start sending advertisements there. So it's a lot of code that you still have to build yourself, much more than when you're working with Bluetooth on iOS and Android. But it's much less than the other 2 options you saw before. And these addresses and stuff that I just showed you here, those are the same regardless of which method you use for interacting with dbus. So if you want to read more about Blues and how that works, the different addresses and interfaces and stuff for the different parts, go to blues.org and you find it there. Oh, beware, it's a lot. It's a lot to read in. And also you need to understand Bluetooth. So, but what about this communication? So someone shouted out MQTT, and that's absolutely correct. That is one of the options. But we have some challenges here. So a lot of time, the latency here can be very low. If it's a device that's not on your home Wi-Fi, it probably has a slow 4G connection. Even like your phone has better, if it's only 4G, it still have a better 4G connection than these devices because it goes on the lowest priority and lowest band and everything. So you can't really do fast connections here. Another problem is, especially if they are not powered if they're battery powered, is they go down into standby and low power mode. So when it goes down in standby low power mode, it needs to retain the network connection so that the server can wake it up. So that's a little bit of a challenge here. You need to set this socket that you have between your device and the backend. You need to have a long timeout on that one. You need to send occasional keep alives, but not too much to drain the battery. Finally, like the buffering is a problem here. You can't just spam a lot of messages on it because eventually, because of the slow connection and it might be in standby, you might just flood the buffer and it won't receive anything. So those are the challenges you have. Now, the alternatives here, like HTTP2 can be an alternative if it's a like Wi-Fi connected device and powered, so it can be full powered all the time. Then HTTP would work fine. You take an HTTP connection, you have a server sent events socket where you receive messages from the backend. That's fine. But most of the time, if it's battery powered, that's not really an option. So the other protocols are these. There is one called Constrained Application Protocol, or CoAP. It's a little bit older, and it reminds you of REST interface, but it also supports something called Observe. I wouldn't recommend this one now. So instead, what has happened is there is something called Lightweight Machine-to-Machine Protocol, which is a newer version which builds upon CoAP. So don't go for CoAP, go for the lightweight M2M instead if you want to go that route. It supports both publish subscribe model and client server model. So both of those works. The other one is MQTT. An important thing if you choose MQTT, you choose MQTT version 5. Not 3 or anything older than that. You use 5, because anything older than 5 is not really suitable. Despite the name, it does not do message queuing. MQ comes from the old days when it was created by IBM and their MQ series products. So it's called, like the unofficial full name is MQ Telemetry Transport. And telemetry is basically what it's all about here. It's sending like small messages. It's well designed for very constrained devices. So it's not a huge chunk of data you pass with this one. But it's still a good protocol to use in many cases, especially if you don't need to pass a lot of data. And finally, we got Advanced Message Queuing Protocol, or AMQP. And that also works fine. MQTT only supports publish-subscribe model, not the client-server type. AMQP supports both, like client-server and publish-subscribe. So that's the advantage of that one. It's a little bit higher level protocol. You can do more with it. So depending on your use case, either lightweight machine-to-machine protocol, MQTT, or AMQP. I can't decide this for you, so it depends completely on what kind of device you're working with. For MQTT, in the Kotlin JVM world, there is the PAHO library. I think that's how you pronounce it, PAHO. It's Eclipse project. And, well, it's fairly simple to work with. Nothing strange here. You have topics. So the typical thing is that you have a topic that's where you receive messages, and you have a topic where your device publishes messages. And you build it that way. That's one way of doing it. There are other ways to design this. Then you set with this one, you set a callback, and then you can send. You can pass messages, and you receive messages, etc., etc. So, not very complicated to work with. Works fine, and it has a lot of options for retries and reconnections and stuff like that. So it's very suitable for this kind of thing. The AMQP library is a wrapper for RabbitMQ library. So it's a Kotlin wrapper on top of a Java library. But it's also super simple to work with. It has a little bit nicer Kotlin syntax. So you pass the connection string, and you got this, you put the callback here when you receive a message, and you have a method for sending message where you publish it there. So pretty similar in the way you work with it. So both of these libraries, when you're on the Kotlin JVM. There is also an MQTT library, which I haven't included here, which works for Kotlin native. I haven't tried it. If you just Google it, you will find it there as well. So if someone tries it out and have some experience with it, please let me know. For lightweight machine-to-machine protocol, there is another Eclipse project called Leshan, and I haven't used it, so I'm not going to show you any code because I didn't have time to test it really. But I'm expecting that one, the experience there, to be on par with what this MQTT library here has. Okay. So, cool. We're ready to go. We got the alternatives for how to communicate. We got the alternatives for like communicating with between the smartphone and our device. And so, what's left? Well, most of the time it looks like this, right? You're not at home, so you can't use Bluetooth to talk to your device. Your robot vacuum cleaner, you can't connect with Bluetooth to it, so you need to go through the cloud. Here's a problem then. So if you would do something like this, you would bounce it through the cloud. You will use like this MQTT or AMQP or something to send a message. It goes to your cloud service, and that pushes it down to the device. So the round trip here is basically like this. All the way down to the cloud service and down to the device and back. And if this now is a very slow 4G connection, we get long latencies, long calls here. The user experience will be really terrible. Also, we will waste a lot of data. If you think of something like, get me the current status of the device, if I need to call that every time down to the device, most of the time the status have not changed, right? So we only want to send a message to our IoT device when something is different, right? We only want our device to send the status when something has changed. So the way you do this is called digital twin. So basically, we take a digital representation of the device in the cloud, and that's the one your app would talk to. So the device instead now, whenever the state is changed, then it pushes a message, and our app would just talk to the digital twin instead. You will save a lot of data traffic on your thing. You will reduce battery consumption because you will not send unnecessary messages down to it and wake it up. So this is almost a requirement when you're working with IoT devices where you have mobile connections like this. So another big challenge. Those of you who have tried to set up a smart home device, you know this Wi-Fi setup thing is super annoying. So you get this like, okay, enter the password for the Wi-Fi. And you're like, got this really shitty UI, and you have to remember the password for your home Wi-Fi, which you never entered in 3 years, and things like that. So that is a challenge. It's a user experience challenge. We know that this is where a lot of the installations fail when it comes to smart devices at home. So how do you do this? How can you get your smart device to connect to the right Wi-Fi? It doesn't have an interface to enter anything. And those of you who remember the good old days when we had our routers had a button, say WPS. You could push that one, and then other devices could just connect to it without any authentication at all. Awesome standard. It's deprecated. Don't use it. So how do you do it instead? Because we want something that is secure. We want something where we don't have to enter the password, because we have the password to the Wi-Fi on our smartphone, right? So we want that password to be sent over to this device. And there's a standard for that one called Wi-Fi Easy Connect. I love how the Wi-Fi Alliance homepage is really, really horrible in terms of marketing. They're trying to push this standard a lot, but it's not really coming through, which is unfortunate. I think it's partially dependent on few people know that this exists. But the standard is called Wi-Fi Easy Connect, or Device Provisioning Protocol. And this is how it works. You have a URI. This is a URI. The bracket stuff there are placeholders. So what you start with DPP, capital letters, colon. And then comes a bunch of key value fields. So K, in this case, stands for the key for signing, that's specific for this device. That you will use to talk to the device. M stands for the MAC address or a hardware address for the device. And then you have a bunch of other fields. A here stands for like, how did you get this URL? Q as a value to A means QR code. So that could be a QR code that's printed on the box or on the device that you scan with your phone. And then you have S, which means how would we provision this device? How will we send the credentials? And there are a bunch of different defined standards. Wi-Fi is one of them, most common. They can also do it with NFC, USB, or if the device has a camera, it can be a QR code as well. So there are different ways to do this, defining the standard. There are also possibilities to use out-of-band stuff like Bluetooth, but that's not covered by the standard. Wi-Fi is the most common way, and that's usually what's supported by your phone as well. And it works something like this. So when you use the configuration of Wi-Fi, so the configurator, which is your phone, you scan this code, this URI, usually as a QR code somewhere. And then you connect with a Wi-Fi to that device. You've probably seen this one where you get a pop-up in the system saying, do you allow this app to connect to this Wi-Fi for this device? That's when this happens. And then you get an auth response back saying, okay, yes, you're allowed. You send the right key and everything. Please proceed. And then you exchange a session key here. And then the configurator, your phone, will pass this over the credentials to the device. And then the device will connect and say, okay, I'm fine, I'm good, I'm connected. We can continue over the regular Wi-Fi. This is supported by both iOS and Android. And on Android, you do this. You have an action process Wi-Fi Easy Connect URI, and you pass this URI that I showed you, that you got from the QR code, and then you say start activity for result. Awesome. And with iOS, we're using Kotlin Multiplatform, of course. So basically, you set up an any hotspot configuration where you pass in the URI. You tell join once is false. This is not just a temporary connection. And then you say apply the configuration to the any hotspot configuration manager. And that's it. The system takes care of the rest. So both iOS from version 13 and Android from version 12, I believe. I might be wrong, but check there. Both of those support this. And this means that the user does not have to enter the credentials manually, which is pretty awesome. It makes for a much better experience. And if you are working on an IoT device without any way of inputting credentials, definitely look at this. How would we do it on the embedded Linux side? Well, so the great thing here is that this uses Unix domain socket. It does not use dbus. It's a VPA supplicant. That's a standard way of doing Wi-Fi stuff on Linux. But you connect to this Unix domain socket. Again, you need Java 16 or later. So you connect to that one. It's basically like you treat it like a socket. And then you send commands to that socket. In this case, first you say bootstrap, type QR code. These first two here is for generating the QR code if you want to generate it on the fly. You could skip those, the step 1 and step 2, and have that hard-coded instead, and then have everything configured that way. That's also an option. But this case here, we might generate a QR code that might be shared in some way. But the final here where you say, please start listening for incoming requests, basically. And then the VPA supplicant will do the rest for you. Okay. Other important stuff here that I haven't covered yet is like, once you have everything up and running on your Raspberry Pi, you want to package this one so that you can easily flash a Raspberry Pi or whatever hardware you have. And there are two options here. One is called Buildroot, and the other one is called Jocto. These are two ways of basically distributing Linux embedded Linux firmwares. When you're working with embedded Linux on these types of hardware, you don't use apt install. You don't use like these things. It's not Reddit or Debian. It's a completely different kind of Linux. So the two tools that are there are Buildroot or Jocto. Those are like complete different presentation sessions by themselves. Doesn't have anything to do with Kotlin, so I excluded it here. There are really good guides for both of these. But yeah, those are the two options you have to choose. Now, I haven't talked about smart home integration much. I had planned to, but the thing is, I don't think this standard is going to work out. I see anyone here remember the standard called DLNA and UPnP? Some of you here raise their hand. Yeah, I have the same vibes about Matter and threads. I see the same thing there. They are implemented, but they're really not working compliance-wise. Another interesting thing that I just started looking at that I'm not an expert on this one, so this is why I didn't start to include anything of it in this talk, is about the JVM tuning. If you choose to run the JVM on your embedded Linux device, you can either just run the hotspot VM just regular there, or you can look at the Graal VM. But both of those are the options for running the JVM. I'm really curious about how the Graal VM behaves running over a very long period, but also how would the ARM version of the JVM work. So both of those are really interesting topics that I'm going to explore more. Also, not really related to Kotlin per se, but maybe next year. Yeah, I have 10 minutes left. Wow. Anyway, summing this up, there are two options you have to start with thinking if you want to go into this field here. Kotlin native or Kotlin JVM. Both are valid, both works, but one is more limited, of course. The other one, easier to work with, but also more resource consuming. You need to learn how to use dbus if you're working on Linux, especially if you want to do anything with Bluetooth. If you're not going to do anything with Bluetooth, maybe you don't have to use dbus, but it's probably good to know this one anyway. There are no good ready-made libraries for this yet, but maybe we'll see it soon. It should be possible to do a pure Kotlin library for this. The protocols for communication, there are 3 ones you have to pick. There is lightweight machine-to-machine protocol, MQTT, and AMQP. Those 3, Sorry. Both of those are perfectly valid. So they provide, like MQTT is the most low-level one, and L2M2M and AMQP is more application-level protocols where you can do more. Most likely, you will want to build some kind of abstraction on top of that, an abstraction that also works when communicating over Bluetooth. Now, the final thing is that provisioning is an important part. A lot of time I see this one being skipped and being like kind of an afterthought. So if you're starting up with some IoT project, even if you're not using Kotlin, learn how Wi-Fi Easy Connect works and device provisioning protocol and how to enable that one for that device, because it makes a huge difference for anyone who's going to set it up later, especially if they're not very technical. Okay. Thank you so much, everyone, for listening. I think we have time for questions.